coming tonight. My name is Greg Murray. I am the chair of the Political Science Department, and we in Political Science in Augusta University are really excited about welcoming Dr. Margaret Kosal to talk to us tonight about bioterrorism, biodefense, and you can read the title of her talk there. Her webpage that you saw, if you saw any of the links, is quite modest in terms of her accomplishments. She's going to go over a few of them there. I know Maggie from an association that I'm involved with that she is also involved with, and she's getting ready to be the incoming editor for Politics and the Life Sciences, so we're glad to have her bring her expertise to that journal. And without further ado, I will turn the floor over to Dr. Margaret Kosal. Thank you.
Thank you, Greg. I very much appreciate the opportunity to be here. Talk a little bit about some of my research. So I'm going to be talking broadly about the intersection of technology, strategy, and governance. And this comes together in WMD, Weapons of Mass Destruction, and emerging technology. Sort of a brief outline, give us a map of where we're going to go. I'm going to give you a little brief background, some of my bio, how I got here, how I got to the place where I have some authority to speak to these issues. We're going to talk about research motivation. You know, where am I situating this within a broader research agenda? Policy relevance. Something that's very important to me is what does my work mean in the broader context of potentially being implementable and executable for whether it be national level security or international level security. So we're going to talk about some of the weapons and threats and case studies. This evening I'm going to focus in on 3 case studies having to do with what I call high tech. A few of you tomorrow may be in the class that I'm going to be speaking to. I'm going to be emphasizing the low tech side, and I've got low tech in those sort of air quotes there, because often it is co-option of civilian technology, things that we think is being fairly low tech that can have huge consequences. How many of you heard about the DDoS attack that occurred this past week that was leveraging the Internet of Things? So there's pieces that are part of our technology, including things like DVR players, I bet some video cameras, to execute a cyber attack. We'll talk about some governance issues, and by governance, I'm going to talk about everything from a few things that are sort of more informal to getting to some of the international arms control treaties and the major legal aspects, and then conclusions and future directions. So my goal is to do this all in about 40 minutes. If along the way you have questions, you know, especially if they are questions of clarification, please feel free to interrupt so that we can engage and make sure that that confusion is minimal. Okay, so how did I get here? So in many ways, I'm a bit unusual for a professor of international relations. We call it international affairs at Georgia Tech. My background, my PhD, I'm actually trained as an inorganic experimental scientist. My PhD was in chemistry, and I spent most of my doctoral dissertation designing, synthesizing, characterizing, and studying the reactivity, if you want to think of molecule-scale tinker toys. From that, eventually I became co-founder of a small startup company, ChemSensing. And this, in some ways, was part of what got me interested in asking questions about science policy in a more robust manner. As a freshly minted PhD, I thought I knew better. Why is the NIH funding this, National Institutes of Health, when I thought they should be funding our research in bioterrorism detectors, chemical terrorism, explosive detectors. So I made probably a 90-degree, 120-degree shift and went from experimental scientist and entrepreneur to security studies scholar, or sort of a technology security studies scholar. This intersection of technology and international security. Sometimes I call it a knife edge. As I was finishing finishing up my time at Stanford CSAC, which is part of the political science department out there, I started to look at where might I go to continue doing the work I'm doing. And to be honest, eventually I wanted to get back to an academic position. But it was like, well, how do I make myself credible to a political science department? Well, one of the ways you can do that is you can go make policy. I mean, another way is to become a PhD in political science or IR. The opportunity came up for me to go serve in the Pentagon, what's called the Office of the Secretary of Defense, and I served as the Science and Technology Advisor to the Assistant to the Secretary of Defense for Nuclear and Chemical and Biological Defense. Try putting that on a business card. It becomes S&T Advisor to the ATSD-NCB. By the way, working in the Pentagon, you learn a new language, Pentagonese. Don't get foreign language credit for that. So I've done a number of things. That was 2005 to 2007. More recently, I spent a year as a senior advisor to General Ray Odierno, who at the time, he was the Chief of Staff of the Army. Normally, that's the highest ranking Army officer, but at the time, General Martin Dempsey was the chairman of the Joint Chiefs of Staff, so he was technically the highest ranking Army officer in the U.S. Odierno was the second highest. And I worked on a variety of different things. In particular, when I was in OSD, I was working on a lot of science and technology investment. I thought I understand the military. Then you go to the Department of Army, and it's like, wow, their approach to WMD, CBRN, very different. So I leveraged this experience in terms of my work, and the research questions that I'm really grappling with ultimately are understanding and explaining the role of technology in politics and war. And just as much I'm interested in the role of politics and war and technology. That is, I don't want to be technologically deterministic. You know, it's not that technology necessarily drives. They go back and forth. This is a illustration from an article from almost 2 years ago, Proceedings of the National Academy of Science, one of the leading journals, peer-reviewed journals, in which Turchina and colleagues were actually looking historically at the emergence of, they call them polities, basically you think of the emergence of civilization. And looking at the emergence of civilization and how that correlated, so they're not necessarily saying causal, correlation, how it correlated with the emergence of certain groups of technologies that had utility in war. So there are two pieces that I want to pull out there that are going to be relevant for what I'm doing. Groups of technology. So it's not a single technology. And when we talk about biotechnology, when we talk about nanotechnology, talk about cognitive neuroscience, these are not a single technology. They are groups of technologies. And then the other piece is that had implications for war. You know, so at this point, as an international affairs scholar, I ask, well, was it actually their implications in war, their asymmetric advantage that they gave, that was the important piece in terms of creating these hierarchical structures? You know, that's the broader question, sort of putting in my broad research agenda. Bringing it back more to international security, I'm also looking at things like offense-defense theory. Offense-defense theory is a dominant theoretical explanation of framework that arose in the time of the Cold War, so realists in terms of IR scholars, to explain the relationship between technology and conflict, really instability and stability in the international sphere. Well, one of the pieces is challenging in thinking about the Cold War. You're thinking about nuclear weapons, you're thinking about missiles, you're thinking about tanks. Well, what happens when we start thinking about nanotechnology? How does it work within offense-defense theory? And I actually assert that at this point, it's challenging offense-defense theory in terms of explaining instability and stability. So get a little more detailed, the kind of things that I'm looking at broadly are these security puzzles. That is, do these emerging technologies have some unique strategic value? So one of them up there is nanotechnology. Anybody know what is the single largest commercial sector for nanotechnology? Yes? Cosmetics. Now, there's everything right with that from the perspective of capitalism. But is that a strategic application in the sense of it having national security implications for the United States, our allies, and potentially our adversaries? No. Now, there are applications of nanotechnology, and most of them actually have become much more embedded rather than sort of individual pieces that certainly might have national security significance and may potentially have strategic significance. But pulling this out, what is it about a technology and does it do this? And then how do these technologies affect conflict and cooperation? I'm very interested in looking across the spectrum of what are the identifiable technical pieces, that is literally the physical material, as well as the knowledge, both the explicit knowledge and then what we sometimes call as the tacit knowledge. Because all of you could read an experimental procedure. Probably most of you could not repeat an experiment. Most of these days being 10 years out of a lab, I can't repeat an experimental procedure. Structural, organizational, and I think this is a huge piece in explaining and understanding how, especially these technological programs in different states. You look at the way the United States does National Nanotechnology Initiative and what has come out of it, comparing it to Russia. The Russian National Nanotechnology Initiative, their version of it, Rusnano, is situated in something called the Kurchatov Institute. Anybody who's familiar with the Cold War knows that the Kurchatov Institute was also where they did a lot of the basic research, the cutting edge S&T related to nuclear. You have literally, not metaphorically, guys who, during the Cold War, were nuclear health specialists who now have just changed their nameplate and have become nanotechnology health specialists. They're also getting old. If you were doing that during the Cold War, before 1991, and you were doing this in 2007 or 2013, these are not, these are people who are going to be retiring soon. So something there also about the structure of organization in terms of demographics. And then the political and ideational factors. And how do these things interact? So a whole bunch of things have to do with sort of perception and ideation versus technical reality. And then how does that influence which institutions? How does that influence things like Congress? Because Congress can be influenced by politics. I know that comes as a complete surprise to political scientists. But how many scientists does anyone think are in Congress now? It depends on how you count them. There actually is, there's a woman from Pennsylvania who has a background, she's a geologist, and there's a physicist in Illinois. There used to be a physicist from New Jersey. He retired and is now president of the American Association for the Advancement of Science. There are a whole bunch of MDs. Fortunately, many times.
They don't count.
As we think about these different pieces, and then again, governance. How do we deal with our own ingenuity? Okay. Another way of looking at these is what is the different type of environment that we're in? And where I'm going to be focusing today is mostly on this area. This slide is completely stolen from David Perkins, who's Commanding General of U.S. Army TRADOC. So the disrupt quadrant, those are really where you have a complex environment with peer or near peer competitors, this high-tech side. But we're also very interested in that quadrant in which you have emulation. And those is where you have non-state actors, regional threats, who might not have the same technical, organizational, monetary funding capability, but are interested in figuring out how they can leverage our own technology against us or mimic things. A huge driver, I would assert, when we are dealing with issues of emerging technology, particularly in the policy realm, is uncertainty and complexity. And the policymakers want to avoid technological surprise. So I have 4 quotes there, one from each service so that I'm not showing any bias. Also over time. And I want to emphasize, so here we've got one, David Jeremiah, he's talking about the balance of power. So how does technology affect this idea, balance of power, very fundamental political science. Robert Keller, at the time, he was the commander of STRATCOM. That's the combatant command that came out of Strategic Air Command, essentially the guys who are in control of the nuclear weapons. He was asked, what is he concerned about? And it surprises what keeps me up at night. Robert Cohn said something similar. Are we going to miss something of the adversaries? In many ways, all of these go to ideas that NATO articulated in its first strategic concept, New Strategic Concept Review. This was the first major review of the North Atlantic Trade Organization. North Atlantic. Treaty, thank you, I'm like trade. Treaty organization since the fall of the Soviet Union. They highlight these technologies, and then at the end, what they're talking about there is balance of power. The concern is how might one of these shift balance of power from NATO nations to an adversary nation. Okay, I'm going to skip this in the interest of time, and I want to start talking about some of the science underneath here. So we'll have a whole bunch of different contentious research. The image there, Ron Fouchier, he's actually a Dutch researcher. H5N1 is an example of a flu virus that was made more transmissible, essentially so that more people can be infected human to human. It was done in a ferret model. One example, synthetic polio, mousepox, or a couple other examples I'm not going to go into. I want to highlight this dual-use conundrum. If any of you are philosophers or historians of a certain era, dual-use conundrum at one time was defined as, does the technology have a use for military versus civilian? In biosecurity and in a more modern usage, it isn't defined on whether or not it's civilian versus military. It's what's the intent. One can use a technology, one can be employing a technology, particularly in a research environment, to develop better countermeasures, develop better protective measures. That's an acceptable thing to do under the dual-use conundrum, as opposed to be using technology for deleterious purposes intentionally to harm people, animals, plants, agriculture, critical infrastructure. So a project that I've got going on now, I'm asking this question of, are there any technologies out there, looking at biotechnology, that have the potential to compete with nuclear weapons in terms of strategic stability? Strategic stability is this concept that comes out of deterrence, the Cold War. Really, strategic stability, you were talking about nuclear weapons and balance of power, ability of one power to deter another. So if one looks at biological weapons of the 20th century, the answer is no. There are no biological weapons of the 20th century that compete with nuclear weapons. And certainly a reappearance of smallpox, while that would be horrendous, we would survive a reappearance of smallpox. We survived smallpox to begin with. It would not destabilize as such to be an existential threat. So if I start thinking about what might be an existential threat and how might this come about, I look at something called CRISPR-Cas9. Anybody heard of CRISPR-Cas9? Okay. CRISPR-Cas9 is a gene editing technique. It is not the only gene editing technique. There are a couple others called zinc finger nucleases and talons. What those gene editing techniques do, different than previous ones, and what CRISPR-Cas9 does is it's much more efficient, it's much more targeted, and it's a lot easier to do. To the extent that you can do what are called germline changes. Germline changes are where you cause an organism's offspring to be changed. This has been done with a variety of different animal models, some small animal models to things like salmon. It's been done in monkeys, which is a close model, where you change the germline. Now, it is not legal to do this in the United States. This paper came out past summer, and this was the first time in which anyone has reported attempting to do a germline modification on human embryos. It's a Chinese team. They're in Guangzhou, sort of southeastern China, and they report this. They had these embryos that they obtained from a fertility clinic. They were embryos that they asserted were not viable, and they attempted to edit, to make this germline change. Started out with 86 embryos, 70 of them survived, 28 were successfully spliced. One of the things they did observe were what they call off-target mutations. Mutation didn't happen where they intended it. But you're looking at this, here's a technique, and one can start thinking about a scenario in which if one was to target the germline of a nation, of people, in such a way that a nation could no longer produce offspring. That's the ultimate existential threat, one short of actually killing off everyone. So if one could demonstrate that, there you have a technology that competes with nuclear weapons in terms of strategic stability. Now, there is one crucial difference. Nuclear weapons, we have this means to get them. They're ballistic missiles. We have a means to get them. At this point, we do not yet have the means to, or what are called the concepts of operations. The delivery mechanism, the concept of operation for deployment. Certainly don't have it in biotechnology. It might be in engineering. It might be in the engineering that we're not thinking about. So this is where one has to make choices as to what you talk about in a public setting. And I am very cognizant of not unintentionally giving out information that, trust all of you are good, upstanding Americans. But sometimes I give talks in other publics, and one always has to be cognizant of that. So being, as a scholar, some reflexivity in terms of what I do. Okay, so I already mentioned the United States, germline editing, talking about sort of, yes?
Before you move on to
Yes.
this side, I'm just curious, what was the team trying to do?
This team?
Yes.
They were trying to edit the germline
To do what?
to change this one specific gene, because it has, so this protein, this beta globin protein, it is associated with a certain disease. So that's, talk about the dual use,
Yeah,
really good thing
intent.
to bring up. So there's a lot of research being done on here, done in CRISPR-Cas9. For example, can we change an individual's DNA so that you don't have sickle cell anemia, so that you don't develop Alzheimer's? So there are a number of genetic diseases. Sickle cell anemia happens to be the one that has recently gotten the approval for what's called clinical, that is for a single person who wants to do their own, not the germline editing of the offspring. So all of this research that we're talking about now in terms of what's being actually done. It's being done for good reasons. You know, the question here is, well, first of all, you know, we're looking at an area where there's concerns about ethical issues, there's concern about moral issues, and there's also concern about, well, what else might this be used for? Great question, thank you. When I was looking at governance policies, laws, especially around the world, tend to find very strict policies in the United States, Western Europe. Many countries might have explicit legislation, but then there becomes the question of, do they have a tradition of rule of law? Is this enforceable? China's a great example where there's a lot of problems with rule of law. They have a lot of legislation, but you often don't have it actually implemented. And gain of function work, and this is sort of describing this area broadly of work, may not be done at the state level. And I use an anecdote, an example, it is an anecdotal example. There's a country in Southeast Asia that has a small startup in it. And this startup company is making botulinum toxin last longer. So botulinum toxin is a toxin. It was part of the former US, part of the former Soviet biological weapons program. Botulinum toxin is one of the most deadly toxins. It also is used for Botox. And so this company was making botulinum toxin last longer. So instead of getting whatever it is, 4 Botox or 6, I don't know how many, I have the wrinkles, treatments a year, you might only have to get 1. This is being done at a small company in Southeast Asia. It's not being funded by a government. It's not being done in any sort of military lab. It's not state level work. And, you know, again, they've got a reason. I'm not sure that that's sort of a real defensible reason, but they do have a reason that doesn't say we're actually making this so you can make a biological weapon. And when one's thinking about these issues, one cannot just look at states. One certainly cannot just look at universities. And then you also can't just look at what are the laws on the books. Because just because there's a law on the book does not mean it is necessarily enforced or implemented. Move ahead there. I want to talk about another gain of function experiment that was done. This is back to the Ron-Fouchier, which is the H5N1, or as we like to call it, the ferret flu experiment. So there actually were 2 papers. Ron-Fouchier and his group in the Netherlands wanted to publish in the Association for the Advancement of Science, an American journal called Science. And there was a researcher in Wisconsin who had demonstrated the same thing, a different method, who wanted to publish in Nature, which Nature is the leading journal in British science. Both of them showed increased transmissibility. The Wisconsin researcher was actually using a slightly different model. And they'd shown that they could do these modifications to the virus, and it became more transmissible. Ferrets happen to be the human model. Their lungs and whatever the system seems to have some parallel better than other creatures. So they wanted to publish both of these, and in the United States, journal editors who are completely separate from the government, nonetheless saw this, came in and was concerned about it, and bumped it over to the National Institute of Health, has something called the NSAB, National Science Advisory Board on Biosecurity. Purely advisory, but said, here, what should we do about this? One of the responses after they got the advisement to not publish from the NSAB was flu researchers self-imposed moratorium. Now, in looking at this, so here's one lens, talking about our Congress critters, excuse me. congressional representatives. So Sensenbrenner. I am not convinced that we have implemented the necessary precautions to protect Americans against biological attacks. We have to balance national security considerations with the necessity of allowing scientific research and ideas to flow freely. Ad hoc system, which is kind of what's in place, that selectively identifies dangerous research only after it's completed is insufficient. Well, there's some problems with that. And Greg and I were talking about this over coffee earlier this afternoon, is that when you're doing scientific research, often you do not know what is going to happen. I mentioned the monkeypox, experiment in which they intended to cause, it's actually rabbits, to become infertile. Well, it turned out, yes, they were successful in doing that. They also caused the rabbits to die and were no longer affected by the vaccine. So this idea of only after it's completed, nobody has a fidelity of crystal ball to predict that well. That's just not the way science is done. But here he's asking somebody to have a perfect anticipation of all research. Now, and also an ad hoc system, well, guess what? This ad hoc system, I don't know how ad hoc it is at this point when you've got a federal advisory board. It worked. It's worked before. But nonetheless, this is the politics that are being put forward. Scientists responded as scientists do, given the proceedings of National Academy of Sciences, where they talk about it in terms of fear needs to be put to rest with solid science and not speculation. Well, I'm not really sure that the problem so much is an issue of knowledge, and this is not the piece that's going to address it. And this is also very technologically deterministic, very scientifically. Now, there were some scientists who were, the top two, who were in support of increased oversight. So you got Paul Keim, he is probably the world's expert actually on anthrax. Lisa Murillo, I actually don't know her, but she's affiliated with Lawrence, Los Alamos National Laboratory, who, again, are not sounding that different, especially Murillo, than Sensenbrenner. And this is the one that I find in some ways more interesting. So Alexander Kella, he is an international relations scholar. Currently he's actually at the Chemical Weapons Convention, the implementing body. Baffling is the absence of any reference to the Biological Weapons Convention in this international discourse. Well, to me it really isn't baffling because the Biological Weapons Convention is an incredibly weak treaty and nobody violated, there was no weapon that was created, so why are we, that is not the point of discourse where you're going to have the entryway. Another piece in this, in some ways, goes back to that predictability. This was an experiment that was published shortly after the moratorium was imposed. One of the co-authors from Georgia Tech, repeatability and contingency in the evolution of a key innovation in phage lambda. Okay, what they did basically is the same thing that they did with the flu virus, but instead this is a virus that infects a bacteria. And just like some of you were rolling your eyes at phage lambda, nobody knows what phage lambda is. Now, it said flu virus in a mammal, but the underlying techniques here have many of the same implications. It evolved to infect its host. Host is E. coli. This is what we're doing. We're changing its patterns of infection. Mutations allowed the infection through a new receptor. So a new way to be transmissibility. Interplay between genomic processes and ecological conditions that favor the emergence of evolutionary innovations. Nobody starts talking about BWC when you're talking about doing things to a virus that infects E. coli. And it's sort of funny, but at the same time, this idea of what kind of implementations? They become, who gets to make these decisions of what are the allowable research? How do you do it? So there are at least 3 different ways that you can sort of bin out this problem. CRISPR-Cas9 is an example of a technique. You know, it's the you might call it the hammer. It's the thing you use. Gain of function, you get transmissibility. That's the incapability, what something can do. Well, then there's another way that you can do it, which is you can do what's called the select agent rules, and that's controlling the bugs. And historically, we've really focused on controlling bugs. And this is very much an adaptation from the Cold War, in which one tried to do something called MPC&A, Materials Protection, Control, and Accountability, in which you would lock up all the fissile material, lock up all the material that could be used for nuclear weapons. So, out on the planet, can you find anywhere, can you go out and dig up uranium or plutonium that you can use for a nuclear weapon immediately?
No.
No. It's like, first of all, plutonium doesn't occur naturally anywhere, and you have to highly enrich the uranium. So when you're talking about it from a nuclear weapons perspective, MPC&A makes sense. You want to lock up, you want to ensure that you know where all the fissile material is. There's a anthrax outbreak right now going on in, I think it's in Kazakhstan, one of the stands. Every year we've got someplace between 10 and 50 outbreaks of Yersinia pestis, the bug that causes the plague, in the Four Corners region of the United States. It's endemic in the prairie dogs out there. Can we lock up all the bugs? No. I mean, we've tried to lock up one bug, and that would be smallpox. The reason we've tried to lock up smallpox is because it has been eradicated in nature, and it remains at vector in the Soviet Russia and the CDC in Atlanta. They have samples. And there are regularly discussions, not as much as there used to be. There used to be regular discussions about we should just get rid of all of the Yersinia variola major strains. Okay, where am I in time? Okay, real quickly I want to talk about, really briefly, a couple examples from nanotechnology. And I emphasize these examples because these are things that circumvent biological countermeasures, but they don't look like what you find in a microbiology lab. That is, if you're designing security measures, you can't just look at the microbiologists. So this is an example, and the underlying science is taken from legitimate real-world science published in real journals, nothing from irreproducible results here. But the specific application that I discuss here, the scenario, is not something that's been done. So we've seen a whole bunch of work done taking these carbon nanotubes, and people have appended, like biologically active cargos. It's fairly easy to do, just disulfide bonds. Different things to them. We've seen that these then enter into the cells, and I see the outline of the cells. This one is an example of a carbon nanotube that has a protein that glows green. That was what they wanted to demonstrate, they could get them in there. You can do other things, and these are the motivation for this research is, well, what if you are tethering to it some sort of small molecule that kills cancer cells? So there's lots of good reasons to do this. So in terms of thinking about a scenario, a dual-use scenario, anthrax, the way anthrax kills you is it actually has 2 different factors, the edema factor and the lethal factor, that are injected into your cells. And the way that they're injected into your cells is the other thing that anthrax, the Bacillus anthracis produces, is something called the protective antigen, PA. And PAs form these little things that look like donuts. These little donuts are what enables that edema factor and lethal factor into the cell. If you just had edema factor and lethal factor floating around, it wouldn't get into your cells. That's needed. What the vaccine targets is the protective antigen. It recognizes that and it stops that from working. So if you wanted to circumvent our countermeasure, you get around the protective antigen. So, I think some of you are starting to already think of well, instead of protective antigen, if you attach the lethal factor and the edema factor to single-walled carbon nanotubes, these now pass through the cell walls. And there you have a means to get it in there. That will not be detected. And it also, the vaccine won't work. So very different work that again has applications for biological weapons or for biosecurity. But we're not using anything that you're really finding in a microbiology lab. Some of these images here, these are taken from a guy who's actually in a chemical engineering unit at Stanford. A couple of folks doing some really cool research are at University of Pennsylvania in the physics and astronomy department. They're designing de novo strands of DNA that then interact with carbon nanotubes as detectors. You don't think about looking in a physics and astronomy lab for individuals. So the models that we're thinking of from, let's skip over these, from the Cold War don't necessarily apply. I'm going to start wrapping up here. Going through this and looking at a number of different case studies, the United States, looking at some things in other nation states, Russia, Iran, Egypt, Israel, multiple states in the European Union, Turkey. We've come up with a number of different metrics for looking at this. So this is sort of coding in terms of what are we looking for in thinking about how to assess these. So there's this question of dual use, offensive versus defensive. In particular, where does it fall along a spectrum? Is it disruptive versus sustaining? So is it doing something new? In particular, is it creating some sort of new weapon, something that might have strategic significance, or is it a nano-enabled traditional biological weapon? So how to think about these in terms of the potential international security implications. We'll go through a number of them in the interest of time. I'm going to move forward. Looking at this more broadly, I've identified a number of key factors. First of all, the deniability and lack of transparency, which leads to instability. Almost everything is dual use. There are legal and cultural norms, particularly when you start getting into scientists and those who are practicing science in terms of behavior. Vulnerability perception. There's a huge perceived lack or limitation of defensive countermeasures. Some of those are true, but some of them are actually these perceptions are driving things. International prestige is a huge issue. I'll use another example from nanotechnology. 2012, I did some interviews in Turkey, including interviewed the deputy director of Turkey's version of National Science Foundation. It's called Nunn. And I had a really nice conversation with him, and towards the end, because I wanted to establish rapport, I asked him what he thought about the assertions by President Ahmadinejad from Iran that Iran was the leading Muslim nation in terms of nanotechnology. And I think he even stamped on the table. No, Turkey is the leading nation in terms of nanotechnology. Nanotechnology and any of these sciences are seen as an indicator of prestige, technical capability, that you can do it, that these nation states can do it. Another example in terms of Iran. For about 18 months, I kept seeing popping up something called FIBIS, Foreign Broadcast Information Service, basically translations of foreign documents into English. And I kept seeing pop up in these ones from Iran, their version of congressional reps, they're called the Majlis, making comments like, the United States does not want Iran to have nuclear technology and nanotechnology. Okay, so they both start with N. What else? They both can be used for weapons. No, I would argue that it actually has to do much more. This convolution of those two has much more to do with prestige. Unquestionably in international security, nuclear weapons in the 20th century were the mark of prestige. At the time, they were looking at nanotechnology as an indicator of technical capability, a mark of prestige. There's no single discipline on which to focus. I think I made that clear. One of the pieces, last week I was in Monterey, part of a FBI, Department of Commerce sponsored workshop on export controls for emerging biotechnologies. It's always interesting to sort of see those who are, what I sometimes call old school, who are talking about microbiology. Microbiology never looked at. If you look around the United States, I think there are like 3 microbiology programs left. Most of them have become like cellular and molecular biology. It's sort of this old school thinking. Whereas I'm looking at this as you might be any place, and I'm also always looking at, gotta watch out for the engineers. They're the ones who make things work. Scientists make things work so you can publish in science. Engineers make things work so you can mass produce it and sell it. Intent has to be balanced with capability. That's a huge piece. And that, frankly, is the piece that we do not do well right now. And if I'm going to advocate from a social science perspective, that's where the social sciences is, understanding the intent, understanding the politics, the history. We got whole lots of people who are scientifically trained who are looking at these and trying to assess the technical side, which is important. I'm not going to pretend it isn't. But intent is a piece that requires those who have understanding of nations, of histories, of the economy, of politics, of these interactions that often are not easily codified through the science literature. I think I skipped here. What we're talking about, I would argue, is mostly a state-based proliferation concern. At this point, the secondary aspect, where I think becomes in some ways more interesting, is this what I call a rogue scientist scenario. Anybody heard of A.Q. Khan? Okay. So A.Q. Khan, he actually was a material scientist. Some people say he was a nuclear engineer. He actually was a material scientist who's from Pakistan, who spent about a decade in Europe building contacts. Then he returned to Pakistan and he became the father of Pakistan's nuclear bomb. He leveraged these contacts for equipment, for capability, for knowledge. Now, according to the Pakistanis, he did this all on his own, considering he had the equivalent of, military jets, military transport planes bringing stuff in for him. I'm not quite sure that if, I went over to Hunter Airfield and said, excuse me, I'd like to have some stuff brought in. But nonetheless, they insist A.Q. Khan was doing this purely on his own. Regardless, here was an individual who was building networks, who at one point at least was largely acting in pursuit of something that he felt very strongly about, that ultimately enabled Pakistan to acquire nuclear weapons capability. Globalization, I provided one example. The private sector is a major player. Most international treaties, international laws are set up between states, state to state. We don't deal well with non-state actors. Legally, states are subsumed under this, legally, private companies are subsumed under their states. But the reality is just as Apple was doing some interesting things with its taxes in Ireland to avoid paying taxes here, companies do interesting things. And all states do not implement or enforce equally. Okay, I think I am, in the interest of time, I'm going to talk more. I'm going to start wrapping it up. Poorly designed biosecurity programs could cripple biological research, frankly, could cripple a whole lot of research, and failed to protect populations against a threat. You know, limiting research in a globalized world, people go other places where they can do it. We also risk hindering our own national innovation. And that becomes a national security impact potentially itself. Can't do the work here, they're doing it in China. Which does not necessarily mean I am suggesting that we should start doing it here. It's that when one is designing a biosecurity program, we live in a globalized world, have to understand the impacts of things here as they may potentially have secondary and tertiary consequences. Gene synthesizers, gene sequencing means samples may never actually be transported. There are no bugs to lock up. The last 2 years, in terms of flu strains in the United States, nobody has actually sent a flu strain. They just send the electrons with the DNA sequence. And then the different labs synthesize that and then use that in their testing. So we have already left the capability of a nuclear model being the end all. Now, again, am I suggesting that we should just distribute smallpox, or am I suggesting that we should just distribute randomly, Yersinia pestis? No. What I am asserting is that limiting it to those kind of biosecurity protocols is not going to be successful. Difference between beneficial and dangerous research is often only one of intent. There's a criticality of understanding the politics, organizational structures, capability, capacity, and tacit knowledge. Many of those things that require technical understanding, but also a whole lot of things that require understanding that come from the social sciences. So with that, thank you for your kind attention on a Monday evening, and I would be more than happy to try to answer some questions, or if anybody wants to challenge me, I'd love that too.
Hey, please feel free.
I should have cut out, 20 more slides.
I've got a question.
Yes.
So you talked about sort of the congressman's reaction to some of this science that's coming out and possibly being published. Are there any actual government structures in place to sort of gag on emerging sort of science that could be published, or entice scientists to bring that into the fold of the government, or sell it to the government or something like that?
Yes. So first I want to pull apart two different things. Of course we've got the executive branch in Congress, and nobody really controls Congress. So one can try and do a lot of work. There are a lot of really smart professional staff members, and a lot of times things are worked through the professional staff members. And frankly, there's a lot of public posturing that goes on that I think can be better explained with domestic politics. And when you start talking with individual people, you will find out that there's actually a lot more together. It's a different part of, I don't do American politics, but that would be my superficial explanation. Within the executive branch, so whether we're talking about the Department of Defense, in particular, the intelligence community, National Institutes of Health, which does lots of biosecurity, to a lesser extent the State Department, Department of Energy, there are lots of very technically competent to technically skilled people. And there are a lot of people who are working on these issues, trying to come up with ways to maximize the benefit to the nation while minimizing the potential harm. Different work people are working at from different angles. Did that answer your question?
Sort of.
What didn't I answer?
Is there any way for the government to stop publication of scientific research?
So yes and no. Certain scientific research already is born classified, and that stops it in the sense that if something is born classified, there are two areas that fall under that. Certain things related to nuclear weapons, and and things are actually arranged, the computing command and control. There's an executive order that was originally put out by President Reagan, and every president since then has reasserted it, which says basic research, that's nuclear weapons and command and control computing, is unclassified. So that's sort of your first level, this executive order. Not as strong as a law, but still out there. Now, in terms of preventing things, so currently we've got this National Science Advisory Board for Biosecurity, and there have been a number of instances, 6 or 7, since 2001, in which research of concern has been brought to the NSAB by the journal editors. And typically it is the journal editors that are bringing it in terms of the publication. Now, does that mean that scientists can't go talk about it? No, we don't have a gag rule in terms of what you're able to say. We have the First Amendment sort of trumps all that. There have been cases where individuals have done things that have for example, the mousepox, Australian mousepox experiment, that was repeated by a guy in St. Louis, never published on it. There are mechanisms, they tend to be what sort of used in soft law rather than...
And a lot of it is sort of self-restraint.
Yeah, it is. It's enormous. Question?
You were talking about, when you started talking and showed a chart on the 4 quadrants and where we were headed, and talk about the nuclear side versus the bio side. And being in the War College, what do you see that when this is all going to really come to fruition? We start to see this starting to happen and be a real threat to our nation.
Emerging biotechnologies?
Mm-hmm.
I mean, when you've asked the $1 million question.
I know that you're all looking out ahead. You've got to be looking down the road. You've got to be looking what possibly the time schedule of when this starts to bring nations powerful, small nations powerful over the large nations.
So in many ways, we're actually already seeing that. And you can look at it, but if you look at something like when the first genetic engineering came about, we had something called the Asilomar Conference, which is notable. And this was when the individuals from the university, from San Francisco State, who basically knew how to do this, got together and they imposed a self-moratorium, driven by concerns with regard to safety and also being good citizens. We live in a globalized world, so you can't do that sort of self-moratorium. When is this going to be? So the scenario that I laid out is a potential scenario to challenge strategic stability. At this point, that couldn't be done, but nobody's crystal ball is perfect. With the rate of technology, 5 to 10 years, it might be possible. So the next question becomes when are, that you asked was when are states going to come together to start doing anything? And I am less optimistic about that. We had a period of time after World War II where we saw a lot of goodwill and effort towards arms control, international treaties. That doesn't exist anymore. Which is not to suggest that I don't see value in arms control and international treaties. I just don't think we're going to see the same level of cooperation. Part of it has to do with the fact that there are players today, many more players than there were after the fall of the Soviet Union, or excuse me, the fall of the Soviet Union, after the end of World War II. Other questions? Yes?
So, knowing that biological records, since you can't exactly contain them since they just spread naturally, knowing how unpredictable they are and how you can't really handle them well in a war scenario, do you think that would make nations more apprehensive to use it, since it might more likely affect their own population, which would decrease the likelihood of a war or a large-scale conflict?
Okay, so it's got a whole bunch of pieces in there, which I think are interesting. So the first one, historically, what you outlined were some of the reasons that nations, including the United States, gave up our offensive biological weapons programs. We found them to not, we considered the traditional biological weapons to not be as effective as other methods, whether it be nuclear weapons in terms of deterrence, or eventually it became conventional military. And then it was also considered that the potential risk, blowback is what it's often called, that risk was too high. So that's conventional weapons. And those never had the same capability. So the question becomes, if you are a emerging power and you want to establish something new, some new way to cement yourself as the superpower, how would one go about de-incentivizing that as a means? And, perhaps even the scenario that I laid out very likely is not going to be the actual scenario. It's thinking about this, because there are going to be new technologies coming forward. And eventually there is going to be some technology that is going to displace nuclear weapons. Perhaps it will have something to do with the cognitive neurosciences. Some people argue it's cyber. I don't, but some people argue it's cyber. That's going to displace nuclear weapons. Something will come up. You may not even know what it is. So the questions you're asking are ones that I think need to be addressed much more robustly. What situations can we anticipate? And then the questions become, what governance models, what things can we do to prepare for them, to be able to deal with them, or to address a nation that might want to pursue it, or a non-state actor. As we're looking at many of these things, the capability is becoming much wider. Other questions?
I'd actually like you to talk about the non-state actor issue with this, because we know that ISIS and the reemergence of the Taliban are doing fantastic stuff with drones lately. We know the Chechens have come the closest a group has ever come to detonating a radiological device, just planted it in Moscow and said, if we wanted to, we could do this. And they didn't do it. I don't know why, but so how close do we, or do we have a way of tracking if these types of sophisticated non-state actors are doing anything? Because that's the scary part for me, because we can't deter non-state actors.
Well, I would disagree. I think you can deter a non-state actor. But yes, there is a vibrant discussion going on. There certainly are probably more people who come down on your side than we can. And where you started out, I think, is in many ways is the fascinating puzzle. Why have we not seen a radiological dispersal device? That unquestionably, that is within the capability of all of these non-state actors. It's basically an IED, but you put some radiological material in it. Why have they not done this? And that, I think, is a fascinating question. Now, to monitoring, particularly in terms of monitoring with regard to biotechnology and biological weapons. It's a very diplomatic, and I use that less in terms of the State Department doing it, and there's tensions. Looking at things like syndromic surveillance. So essentially it's public health monitoring to detect where a disease might break out. So the Ebola outbreak, 2014 in West Africa. A group from Harvard got a lot of press because they said, hey, we detected this way before the WHO came out and said there was no Ebola epidemic. And they did, no question about it. They used, actually social media indicators and some other syndromic surveillance. But what they failed to sort of really honestly, acknowledge was when a Harvard research group, even though it's Harvard, comes out and says something that does not carry the weight of the WHO having an official declaration of an epidemic. So that's what, WHO knew what was going on. They had to work through their own bureaucracy before they made this official pronouncement. So syndromic surveillance, and particularly leveraging a variety of non-traditional indicators and warnings, is likely to be the mechanism by which one may detect, particularly if it's an infectious disease outbreak. Oops, that's went wrong. That's what I was talking. Yeah, so this is proliferation pathways. This is a model that's come out of my group, in which we're looking at, and this is mostly high tech, but you can extrapolate. You know, you start off with a variety of different projects. Not state actors, they don't start out with any initially benign. But if you're looking at a state, most of your projects are going to be initially benign and they're going to remain benign. It's the initially malfeasant. So where do you start looking at detecting these? And you can go through in the different places and sort of identify, in particular, in the major decision points, have places where you can use a variety of different types of indicators and warnings to sort of say, hold on, something's happening here. The classic example, going back to Saddam Hussein, was they looked at these buildings that supposedly were being used for production of pharmaceuticals. And what they noticed was they were looking at the air handling. If you have a pharmaceutical production plant, the air handling is done in such a way, it's kept at a pressure, positive pressure, so that stuff from the outside can't get in. That's the way pharmaceuticals. You don't want to contaminate what you've got going on in there with stuff from the outside. Well, Saddam Hussein, this is going back to the 1980s. This is not 2003. 1980s and 1990s when you had the UNSCOM inspectors. What they had was they had a negative pressure. They didn't want to let anything get out. The outside was the positive pressure so that bugs that they were using in the biological weapons facility wouldn't get out. You know, so that's an example of something that was known, but you can look at it and say, oh, you just told me that's a brewery. Hold on. You've got the wrong pressure. You've got certain things that are wrong. By the way, macaroni and cheese, Kraft macaroni and cheese, actually the sprayers for that cheese stuff, just right about the size that makes good inhalational particles. Now, let's say Kraft macaroni and cheese is a chemical weapon or a biological weapon.
It certainly is.
But again, if somebody says they got a Kraft macaroni and cheese plant, there's something funny coming in and out of there. Shampoo. Shampoo is another thing that actually, shampoo sits in warehouses because there's a activity in which it sort of, I don't know the specifics, the chemistry of it, but you actually have to have it sit for a while. And again, if you're looking at, do they have the same equipment or is something different? So there are all sorts of, but yeah, brewery equipment and Kraft macaroni and cheese, anything you're spray drying, you know, are potential areas, never mind the pharmaceutical ones.
If students wanted to get involved or think about some kind of combination of biosecurity for their future careers, do you have any suggestions of where they could look online for resources or research?
That's a great question. I hadn't sort of thought about that. Usually when I'm giving talks, I say, come join my research group. So what I'd say is, get a research group of students here. The Federation of American Scientists has a number of really good resources. That would probably be the first place that I would send people because it's introductory and it also gives a lot of sort of the background, the history, and as well as sort of who's doing. That'd probably be the first place if you're looking for an online. They've got some really good, also some interactive, if they call them tutorials on that. That'd be the first place. That's a good question. Okay.
Is that it? All right, I have questions, but I get to ask them at dinner tonight, so unless that's it, unless anybody else has anything, we should say thank you to Dr. Kosal.